Marhaba. Okay, in this video we want to talk about what we call naive set theory. Okay, so this is a theory which talks about objects called sets. So let's discuss these entities. Okay, let me start by telling you what is a set. So this is our main definition of this video. A set is simply a collection of objects. Okay, so a set is a collection of objects, full stop. Okay, so you imagine you have some objects, okay, and then these objects you collect them in one bag, say, and this will be the set containing these objects. Okay, these objects, we call them members of the set or elements of the set containing them. Okay, now if we have a set and one of the elements here, okay, it has elements, say one of the, let's call this set capital A, and say one of the elements here is small a, is called small a. So we want to say, we say, okay, A is one of the objects in A, in capital A, or it is an element of A. And to say that A is an element of A, we write A and then this symbol and then the set. So this says that the object A or the element A is an element of the set A or belongs to the set A. Okay? Or if you want to say that set A contains the element A. Okay, so this is how we represent these statements. So we use this symbol just to say that small a is one of the members of the set A. Now, if an object B is outside A, it's not contained within A, then we write B does not belong to A. Okay. Okay, now let's have some examples on of sets. So I want to introduce to you symbols or the notation of writing down sets. So for example, let's collect all the vowels in the English alphabet in a set. So how do we collect? Let's call this set of vowels V. We write the set V is equal, and then we start a set by a curly bracket and finish it by a curly bracket as well, and between the curly brackets we list all the elements in this set. We want this set to contain all the vowels in the English alphabet, which are the letter A and then the letter E and the letter I and O and U. Okay, so this set contains 1, 2, 3, 4, 5 elements. Okay, and this is how we write. We say the set V is the set containing 5 letters, which are A, E, I, O, U, which are the vowels of the English alphabet. Okay, now let's write down the set, say, which contains all prime numbers less than 20. So prime numbers strictly less than 20. Okay, so how do we write this set? We start with the curly bracket and then we start listing all the prime numbers less than 20. So we have 2 is a prime number, 3 is a prime number, 5 is a prime number, 7, 8 is not, 9 is not, 11 is, 13 is, 14 is not, 15 is not, 17 and 19. Okay, so this is the set of all prime numbers less than 20. And how many do we have? 1, 2, 3, 4, 5, 6, 7, 8. So here this set has 8 objects, 8 members. Right, 2, 4, 6, 8. Okay, now sometimes the set contains so many elements that we cannot list all of them, so we use the 3 dot notation. Okay, so for example, the set of positive integers less than 100, okay, of positive integers strictly less than 100. Okay, so how do we write this set? We start again with the curly bracket and then we start listing them. So the first positive integer less than 100 is 1, and then you have 2, then you have 3, and then 4, and so on. What is the last positive integer strictly less than 100? We have 98, and the last one is 99. Okay, so we use these 3 dots, which represent the pattern of this listing. Okay, so this is a set which contains all positive integers less than 100. It contains 99 members or elements. Okay. Now let me tell you another way to represent the set. Okay, let me write it, and we say, suppose S is a set. Okay, then we write the set S is equal to the set of all objects X such that X has property P. Okay, so this is one way to write a set. Let me write it down. So S is the set. Okay, let me tell you how you read all of these symbols. So we say S is the, and then this curly bracket, you read it is the set of all objects X, and then this vertical bar, you read it as such that. Okay, so such that X has property P. So you see what we are doing here. We are making the set S is defined by collecting all objects X where all of them have the property P. So this has property P, all of them have the property P. We collect them all in one bag and call it the set S. Okay, so notice that you can think of this way of defining a set as a club, like a sport club, and the club say this has property P is the membership condition of the set. So let me write it, membership condition. So in order to be a member of the club S, you need to have the membership condition to belong to S, which is having property P. Okay, for example, you can say S is the club or the set of all humans X such that X is a football player. Okay, so this, who are the elements in S? Are those, all of those objects which collect which have the property P, or if you want, which satisfy the membership condition. What is the condition of being a member in S? Is being a football player. Okay. Now let's see. Okay, for short, if you want, we know that X has the property P is a predicate. It's a statement involving the variable X. It's a descriptive statement. We can represent this whole thing by P of X. So another way to write S in this way is to say S is the set of all objects X such that P of X, which means X has property P. Okay, we also can sometimes we replace the vertical bar by a colon. So you say X and then you put 2 dots P of X. But we read it in the same way. So S is the set of all objects X such that X has property P, or such that P of X is true. Okay, so let's have an example to define a set using this method. So look, let's say the set E is the set of all objects X such that X has the following property: is an even positive integer less than 100. Okay, so this is the property of x, that it is an integer, it is positive, it is even, and it's less than 100. Okay, so what is this set? Let's see, let's list all of its elements. Okay, so what are the even positive integers less than 100? Well, the first positive even integer less than 100 is 2, and then 4, and then 6, and then 8, and you keep listing all of them. The last one is 98. Okay, so this is one way to write it, but sometimes we also state the domain of the variable x before the vertical bar, so you can express this set as the set of all integers x. So you say x an integer such that x is even, positive, and less than 100. Okay, so in this way we say we read it as the following: E is the set of all integers x such that x is even, positive, and less than 100. Okay, now let me say an important remark, that sets may contain other sets as elements. Okay, let's see an example. So you could have a set whose members are also sets. So you can look at this set. This is a set which contains the element u and then the element alpha, and the third element of this set is a set. It is the set containing ABC. Okay, and then you have another element. The fourth element is the set containing x and y. So you think of this set x and y containing x and y as one object. Okay, and then the fifth element is v, and the last element is the set containing 1, 2, 3, and 4. And you close the set. Okay, so this set, let's see how many elements does it have. This is the first element. This is the second element. This is the third element. This is the fourth element, fifth element, and sixth element. So this set has 6 members. Okay. If we call this set, let's call it capital A, then we know that U is an element of A because U belongs to A. It's one of the members. Okay, this is a member of A. So we write that the set xy is an element of A because it's one of the members of A. Okay, V is also a member in A, and the set containing 1, 2, 3, and 4 is also an element in A. Okay. Now let me introduce a famous sets in mathematics. We have the set of natural numbers. So we have, okay, just the set of natural numbers. Okay. What is this set? We denote it by this script n, and it is the set containing 0 and all positive whole numbers. So 0, 1, 2, 3, 4, and so on, all positive integers. So the natural numbers is the set starting from 0, then 1, then 2, and then 3, and so on. Okay, so this is the natural numbers. Now next we have the integers. We've seen the integers before. Recall that we represent the integers by the letters Z because in German numbers means Zahlen, and this is the set containing all negative whole numbers. Okay, and 0 and the positive whole numbers. Okay, so -1, -2, -3, -4, -5, -6, and so on. 0, 1, 2, 3, and so on. Okay. Now you have also, say, the positive integers. The positive integers we denote it by z plus, and this is the set of all positive integers. So starting from 1, 2, 3, 4, and so on. Next we have the rational numbers. We've seen this before, the rational numbers. What are the rational numbers? These are, this set is denoted by Q, and this is the set of all numbers of the form m over n, such that m and n are integers. So how do you say m and n are integers? This means that m and n belong to this set. Okay, so we use now our new notation, that belongs. So such that m and n belongs to the integers, and okay, you can use the logical connective and the denominator n is not 0. Okay, so see how we used our way of describing sets to write down the set of all rational numbers. How do you read this? Q, the set of rational numbers, is equal here is the set of all numbers of the form m over n. The vertical bar, you read it as such that both m and n belongs to z, so they are integers, and n, the denominator, is not equal to 0. Okay, we have the set of real numbers, and the set of real numbers is denoted by r, and r is the set of all points on the real number line. Okay, so you have say 0, 1, half, 0.4, you have pi, okay, you have -2, -3.3, you have all the points on the real number line. Put all these elements in one set, and we call it the set of real numbers, and we denote it by r. Okay, so all these points, we put it in one bag, one set, and it is called the set of real numbers. Next, we have the set of all complex numbers. What is this set? This is denoted by C, and this is the set of all numbers of the form x plus I, y, such that x and y are real numbers. So x and y belong to the real numbers, so belong to the set of real numbers, and I is a new number which is defined to be the square root of -1. Okay, this means that I is a new number. It's called an imaginary number, which when you square, you get -1. So this is the same as saying the square of I is -1. Why do I say a new number? I mean, it's not a real number because there is no real number that when you square, you get a -1. So we introduce a new object, we call it I, with this property that the square of I is -1. Okay, so this is the set of complex numbers. Okay, now these are famous sets in mathematics. Again, we have natural numbers. Okay, we have integers, positive integers, rational numbers, real numbers, and complex numbers. Okay, now let's discuss the concept of equality between sets. So suppose you have a set A and you have a set B. When do you want to consider them equal? So suppose this set has star and triangle, and this set has also star and triangle. Well, in this case, we want to consider them equal because they contain the same elements. Now, suppose you have the set C, which contain star and square. Okay, well, we don't want to consider these sets equal, A and C, because they don't contain the same elements. A has a triangle, but C doesn't have a triangle. Okay, so let's define how we want equality to work for sets. So definition, we say that two sets are equal okay, if and only if they contain exactly the same elements. They contain the same elements. Okay. So if you are given two sets and you want to check if they are equal sets, then you open the set A, look at its elements, open the set B, check its elements, and if they both have exactly the same elements, then you consider them equal. Otherwise, if one of the sets has an element which is not in the other set, then they are not equal. Okay. Let's see how can we express this statement, this definition in predicate logic. So let me say two sets A and B are equal if and only if they contain the same element. Well, what do I mean they contain the same element? I want to say for all objects X, so here the domain of the variable X is the set of all objects. If X is an element in A, then we want B to have X as well. So then X is an element in B. And vice versa. If X is in B, then we want X to be an element of A. Okay, so see, we defined equality to be true if and only if the following is true, which says for every object X, X belongs to A if and only if X belongs to B. So this means if X is in A, then it is in B, and if X is in B, then X is in A. So every element in A is also in B, and every element in B is also in A. So they contain the same elements. Okay, let's have an example. Look at these two sets. The first set is the set, so example, let's look at the set of all objects of all natural numbers. So all objects, all natural numbers X, such that X is odd and X is between 2 and 8 inclusive, including 2 and 8. Okay, this is the first set. And look at the second set. It is the set of all integers n, okay, such that n is prime and n is strictly bigger than 2 and less than or equal to 10. Okay, are these sets equal? So this is a question. Let's see when two sets are equal if they contain the same elements. So let's see what are the elements of the first set. Okay, what are natural numbers? These are the numbers integers starting from 0, 1, 2, and so on. We want them to be odd and between 2 and 8. So the odd integers between 2 and 8 are 3, 5, and 7. Okay, so these are the elements of the first set. It contains only 3 elements, 3, 5, and 7. Okay, now let's see what are the elements of the second set. We want n to be a prime number bigger than 2. Okay, what's the first prime number bigger than 2? It's 3. And then 5. And then we want all prime numbers less than or equal to 10. And 7, 8 is not, 9 is not, and 10 is not. So that's it. So the second set also contains 3, 5, and 7. Okay. So we look at the first set, it contains 3, 5, 7, and the second set contains 3, 5, 7. So yes, these two sets are equal. So if this set is called A and this set is called B, so then A is equal to B, and both of them are equal to the set containing 3 elements, 3, 5, and 7. Okay. Now another remark is that what do you think is this set which contains 1, 2, and 3? Is it equal to the set containing 3, 2, 1? Well, yes, because both of them contain the exact elements which are 1 and 2 and 3. So the left hand side set contains 1, 2, 3, and the right hand side set contains also 1, 2, 3. Okay, are they equal to this set? 1, 1, 1, 3, 3, 2, 2, 2, 2, 3. Is this set equal to this set? Is this set is equal to this set? Well, the answer is yes, because the left hand side contains 3 elements, 1, 2, and 3, and the right hand side, like this set, also contains 3 elements, which are 1 and 3 and 2. Okay, so this set, although it has repetitions, but at the end of the day it only contains 3 elements, 1 and 2 and 3, okay, which is equal to the left hand side set. Okay, so moral of the story from this example is that in sets, we don't care about order of the elements, care about order, nor repetitions. Okay, so it doesn't matter how you order the elements or if you repeat the elements. At the end of the day, we only care about the content of the set, and in these examples, all of them contain 3 elements, 1 and 2 and 3. Okay. Again, so if you have repeated elements in a set, you can neglect all of the repetitions and just keep 1 copy of the same object. So you keep 1 copy of 2, 1 copy of 1, and 1 copy of 3. And that's it. So in other words, the identity of a set is defined by knowing its elements. That's it. We don't care about how they are ordered. We don't care about if they are repeated. Just know what are the elements contained in the set, then you know the set. Okay, let me give a definition of one famous set. It's called the empty set. And what is the empty set? It is the set containing no elements. Okay, so you imagine a set and it has no elements. This set is called the empty set, and it is denoted by this symbol or this symbol, curly brackets with empty elements. Okay, now another definition is if you have a set which contains exactly 1 element, say the letter A, this set is called a singleton. It's called a singleton. I mean, any set which contains exactly 1 element, we call it a singleton. Okay, let's finish this video by discussing this. What do you think is this set equal to this set? Okay, so let's see. To decide if 2 sets are equal, we need to see if they have the same elements. Look at the left hand side. This is the empty set. The left hand side, it's a set containing nothing. Okay, let's see what is the right hand side. It's a set containing 1 element, which is the empty set. Okay, if you want, this is a set containing the empty set. Okay, so here we have nothing on the left hand side. On the right hand side we have one thing, which is the empty set. So they don't contain the same elements and therefore they are not equal. Okay, if you want, you can imagine the empty set as a bag. So the left hand side it's a bag. So this, you can think of the empty set as an empty bag. Okay, this is the left hand side. What is the right hand side? This is a bag. So this is the set. It's a bag containing this object. But what is this object? It's an empty bag. So this is a bag containing an empty bag. Okay, so again, the left hand side is, just imagine an empty plastic bag. The right hand side, imagine a plastic bag which contains an empty plastic bag. So they are not equal. One bag is empty, the other bag has another bag. Okay.